Okay, so let's turn our attention back now to major ions. These are the major ions, and the way that we describe major ions is as a concentration of mass per liter. And the way you can visualize that is you could take some water and evaporate it off, and you get rid of the water by evaporation, and the dissolved ions don't evaporate, they stay behind, and they'll crystallize out as solid salts, shown here. It could be sodium chloride, but these other compounds would form different solid materials. And so if you take a liter of water and evaporate all the water and then weigh the residual, you have the milligrams of residual solids per liter of water. Those are the units that are used to express the concentration of concentration of ions. And as a result, we call that the total dissolved solids, when we lump all of the major ions together. And there are different categories of TDS. Fresh water is 0 to, or basically less than 1,000 milligrams per liter. 1 milligram per liter is 1 part per million. Brackish is 1,000 to 10,000. Saline is 10 to 100,000 parts per million, and brine is greater than 100,000. And sea level or sea water falls right in here at 35,000 parts per million concentration of salts. Okay, so if we wanted to measure the dissolved, the TDS in water, we could evaporate the water off of each sample. That would be a way to do it, but that's pretty tedious, and we generally don't do that. As it turns out, though, the charge that's carried by the different dissolved ions, that charge is something that allows current to flow through the water. And so the electrical conductivity of the water is a strong function of the concentration of the ions that are dissolved in it. So if we measure the electrical conductivity, we can correlate the electrical conductivity to the concentration of ions in the water. So we use an instrument that has several electrodes. It usually has 4 electrodes, 2 to apply the current and 2 to measure a voltage drop, and that data then is used to calculate the electrical conductivity. And the way that it works is the electrical conductivity, here expressed in micromos, is proportional to the TDS in milligrams per liter, and the proportionality is this alpha term. So alpha kind of correlates these two compounds. And you see that alpha generally varies from in this range with these units. And you have a bit of variability here because you have some ions that carry 2 charge and some ions that carry 1 charge, and the ions have slightly different masses. So that causes there to be some variability. When you use an electrical conductivity meter to estimate TDS, it'll be set up with a default factor here that's somewhere in this range typically. And then what you can do is calibrate that factor for the water type that you're measuring to get it to be a little bit more accurate. Okay, so the major ions that we've been looking at are just in a general sense. There are some specific ions that are particularly important, really, for different applications. And calcium and magnesium are important because of how they create films and interact with surfactants. And so there are a variety of reasons why this can cause problems, anywhere from affecting how you can shower to industrial processes that might get clogged up by these films. So hardness is a measure of the calcium and magnesium content in water, and you get one number for hardness. It's in units of milligrams per liter, so it's in the same units as dissolved ions. But you lump together both the calcium and magnesium. And the way that you do it is by taking the calcium concentration, multiplying by this factor here, and the magnesium concentration, and multiplying by this factor here to get the hardness. And these two terms, 2.5 and 4.1, they are derived from this ratio, the molecular weight of calcium carbonate to the molecular weight of magnesium, and this is calcium carbonate and calcium. So that what it's doing is it's taking these two compounds and scaling it to a basis of molecular weight of calcite. Okay, so that's just a convenient way of generating this term called hardness. So hardness will be high in areas that are underlain by calcium and magnesium. So limestone produces water that's very hard. And here's the range of concentrations for different hardnesses of water. So if it's less than 70 milligrams per liter, it's considered very soft. And if it's greater than 500, it's very hard. Soft water is 70 to 140, and if it's greater than 140, 210, it's slightly hard. If it's greater than 200, it's considered hard water. Okay, so you've heard probably in common usage saying, okay, well in this area we've got hard water or soft water, or a water softener. And these are some beads that are used for ion exchange, and it's a water softener. And so when you soften water, you're reducing the calcium and magnesium composition or concentration, and you're replacing calcium and magnesium with sodium. Okay, so that's important, and we'll take a look at how you might measure that. All right, so we want to describe these dissolved solids, and what we've seen so far is that we can measure dissolved solids as the mass of solids per volume of water. This is typically how we would do it in the laboratory, and that's how we describe hardness. But we also might use the molality and the molarity, where we're instead of using the mass, we use the moles of the solids per mass of water, and the moles of solids per volume of water. And you probably remember this from chemistry class. And then another important way of expressing this is as the number of charges due to a particular species per volume of water. So for calcium, for example, that carries 2 charges. It's a +2 cation, and so it carries 2 charges per atom, and sodium would carry 1. And so the kind of reactions that occur with these ions, these ionic reactions, depend on the amount of charges that are in the water. And so the equivalent charge, or what's called the Milliequivalents, are a way of describing this. So the Milliequivalents, it's the number of charges per species. It characterizes the role in reactions, and it's important then to be able to convert this mass per volume. That's typically the kind of concentrations that you would get from the laboratory, and so you want to go from milligrams per liter to milliequivalents. And the way that you do that, this is mass per volume. You would divide by the molecular weight of the compound that you're interested in, or the compound that you have a concentration of, and then multiply by the valence. And that converts the concentration from the laboratory to milliequivalents. Okay, the milliequivalents are going to be important because that's the basis for the reactions of ionic species. And then we're going to use that kind of concentration to understand how the water is behaving. So here's a simple spreadsheet where we've got some water samples. Here are the cations and here are the anions, and these are the concentrations that we've got from the laboratory. And I wanted to convert them to milliequivalents and then percent of milliequivalents. So the procedure is you take the concentration here, and here's the valence, the molecular weight, and then you calculate the milliequivalents as this concentration divided by the molecular weight times the valence. So this is just a little formula written in Excel. And you add them all up. This is the total cations and the total anions. And this is like the total number of charges. So you might remember from chemistry that you have to, in ionic solutions, you have to have the charge balance. So the same number of cations as anions. So you can add these up and it should go to 0. In this case, it's not quite 0, but it's pretty close. So the charge balance is used as a check to see how well the charge is distributed, basically to check your analyses. And then what you do is you take all of these concentrations and you scale them by or all these milliequivalents, you scale them by the total. And that gives you what amounts to a percentage. It's a fraction. If we multiply by 100, we would get a percentage. Okay? So here's why you would do this. What we want to do is to take the major ions and develop a way to compare concentrations from different locations. And there are various different types of graphical ways of doing this. And the trilinear diagram is the most common one. So here's the trilinear, and this is the trilinear, so it's triangular really. And here's another triangular one, and then this will be used to compile the data from these two. So the way that it works is this is used for the cations, and this is for the anions. We take magnesium and calcium, and we add together sodium and potassium, and we plot them on this three-sided diagram. The anions are chloride, sulfate, and then carbonate and bicarbonate. And here's how the process works. If we take the analysis that we had previously, and we go to the percentage of milliequivalents. So we wanted to plot calcium. Calcium is 35% according to the milliequivalents in the sample. And so the way we would do that is, so calcium is increasing in this direction, and the way to think about it is it's 0 along that line, and then 10%, 20%, and so on. So it's 30.35. So the calcium, yeah, there it is. Calcium is going to occur right along that line. So there's 20, 30, 35, like that. See how that works? And then sodium and potassium add together about 14. So there's 10, there's 15, 14, something like that. And then magnesium. So magnesium is measured up from here, 20, 30, 40, 50. It goes right there. So this water composition plots at that point right there. And then we do the same thing over here for sulfate, is right there, and chloride is plotted along this axis going in that direction, and bicarbonate is right there. And so the anions plot right there. And then we can extend out these two points to intersect right here, and all of these compositions right here are summarized by that point right there. So it's kind of cool. You're taking this kind of complicated 7 different measurements and you're rendering it graphically. And the reason why we want to do this is because it'll allow us to take water samples from different regions get their composition and compare one to another to see if they're similar or different. I mean, it's going to be kind of hard to tell because you've got all these different compounds, but the way that it's done is to say, well, the region here on these different diagrams is indicative. The region where the points plot is indicative of the type of water that it is. And the term that we use here is hydrochemical facies. So water that it plots in here is in a calcium type hydrochemical facies and bicarbonate hydrochemical facies. And then as it projects up here, it's in these different regions with different hydrochemical facies. So here's an example of that. Here are some waters that were obtained in a region, and what you see is that they, all of the water from, this is kind of color coordinated, but it looks to me like my colors have gotten shifted around a little bit from the mysteries of PowerPoint. These points I think should be over here, and these points here and here. So what we can get from this is we go blue, red, yellow, and here's the key. The blue is peripheral bedrock, and then alluvial fan and salt flats. So these waters were taken out west where we've got some mountain range that has bedrock, and then the mountain range sheds off this alluvial fan, and then out in the middle of the basin is a salt flat. And so the water is recharged in the peripheral bedrock up in the mountains, flows through the alluvial fan, and then discharges or is out in the salt flats and kind of the end of the flow path. And all the while it's doing this, it's changing composition by interacting with the rock. And so what you see is that all of the water that's from the bedrock is plotting here, and then the composition changes as you move in this direction. So you're increasing the sodium-potassium level by going in that direction. And then you go here to the salt flats, and the salt flats are high in sodium and potassium. And so here we see that progression of change from low sodium to high sodium as we go in that direction. And here we're going in this direction, and this is a decrease in sulfate. Here's the chlorides. So the chloride is increasing in that direction. So it plots here up in the mountains, here in the alluvial fans, and here in the salt flats out in the middle of the basin. So as the water is flowing along the flow path, it changes composition, and the cool thing is we go get the concentrations, we convert them into milliequivalents, we get the percentage of milliequivalents, and then we can plot them on these diagrams and see which samples correlate to which samples group together, and see how the composition changes as a function of the distance and the position along the flow path.